Hello, welcome. So, this is a redo of the 23-3 lecture. If you were joining us for the live lecture, it turned into quite a technological disaster. So, this is a little bit of a redux on this and everything else. I'm covering the last problem that I didn't get to cover in the second lecture the first time around. So, if you're watching that sometime later after the first lecture, welcome back. But anyways, for the beginning of this, I'm just going to be kind of rehashing everything that was covered in the lecture like I would have normally. So this time around, we're going to be talking about, at least at the very beginning, certain special electric fields. And alongside of that, I'm also going to start to discuss a few of the things that are going to be going on with dipoles, right? And some of the different things like the revisiting our good friend torque from rotational motion. But before that, I'd actually like to go back to the last slide because that's really kind of where we're going to start here. Our first, what I call a special field result. Right, so we went all the way through these derivations for what's the electric field coming from a vertical rod, right? And ultimately, we ended on some final equation here after we plugged a bunch of things in that looked all right, but maybe not very useful in every single circumstance. But then we asked the question, what would happen if instead of being limited at plus L over 2 and minus L over 2, what if we instead bump this up to plus infinity and minus infinity? Right? What if we got an infinitely long rod, which we know is not a real thing, but if we're in a realistic circumstance where there's a very long rod, then maybe the infinite rod would do a great job of approximating this, if it was easier, of course. And we found that, well, it was actually a pretty easy solution, right? The electric field coming off of this rod would just be 2k lambda over x. Now, we can't quite define lambda as q over L anymore because, well, it's infinite. So that gets a little bit fuzzy, but a charge density is still a thing that even an infinite rod could have. But that kind of had an interesting result because, first of all, it was a 1 over r dependency instead of 1 over r squared, unlike our point charge. But also, it was radially symmetric. That is to say, I could spin the rod around and I would never know the difference, or I could move around the rod, and as long as I maintained my radius, I would see the exact same electric field magnitude no matter what, right? It's just radially outwards. On top of that, I can move up or down, and none of that would make a difference either. So that was our first special equation that we would have, right? So if we ever see an infinite line of charge or a very long line of charge, our infinite line of charge equation can be a useful tool instead of having to derive that through an integration ourselves. Now, we might also see a few others. The first of which is just a ring of charge, right? If I take a ring of charge, so this is kind of a one-dimensional thing that I've curled around all the way, and then I poke a line through it, and anywhere along that z-axis, as I'm calling it here, we would find an expression that looks like this up top. We also have, if this was a filled-in circle, or a disk instead, a similar, slightly looking expression, but some major differences that we can see here. Right, those are just two other very specific, but sometimes very useful tools that we might have accessible to us. Now, one that is going to be certainly a little bit more useful than those two is going to be the plane of charge. And like from an edge view, it kind of looks like the line, but it is going to be quite different actually. We're not going to walk through this derivation, but the end result is you get something like this, where it is eta, which remember is the surface charge density, divided by 2 times the permittivity constant, right? That's little e naught. But this is a really unique result, because not only can I move anywhere along the surface of this thing and I should see exactly the same electric field as before, but you'll also notice there's no y or z or r of any kind. There's not actually a distance dependence when you're talking about the electric field from a surface charge, which is a little bit strange, but I did bring this up about a week or so ago when I mentioned that, sometimes we'll see what we call these uniform or constant fields, and although it seems a little bit strange given what we had seen in point charges, this is actually a thing that we can create, right, within reason. Of course, if we get to the edge of any realistic plane of charge, then yeah, it's going to curl around a little bit, but for the most part, as long as you're somewhere in the middle of this thing, it's going to behave a lot like our infinite plane. What's better than one infinite plane? 2 infinite planes, right? In a shape that we call the parallel plate capacitor. And this is going to be a really important one for quite some time. Capacitors show up everywhere. Almost every single electronics device that you can think of has a capacitor somewhere inside of it. It's just an incredibly useful tool for actually storing charge, right? It's what I call a really bad battery, usually with nastier words than that. But what actually is the electric field inside of this thing? Well, you might immediately think that it's double, but there's a little bit more to it than that. It is double, but only on the inside. Think about the fact that it doesn't have any sort of distance dependence to it. What happens outside of the plates then? Well, if I'm looking on the left here, my positive plate is going to give me an electric field pointing to the left, and my negative plate, being the exact same charge density but negative instead, is going to have a field pointing to the right. Because they have exactly the same charge density but opposite, the fields are opposite but equal magnitude, and they cancel out. And that's kind of another unique feature of these things, is that the electric field outside of them is zero. It's only on the inside that we see this doubly strong electric field, where it's just eta over E naught. Now, I know a few people get a little bit mixed up sometimes about, should this be the eta of both of these together? Should I take the surface area of both of these? But keep in mind, just the single plane at once, you would see eta over 2 E naught. Clearly, this one is just the area of the single plane that we've got, right? Or the surface density. Assuming that this was a finite plane, a realistic plane, we would just have the total charge on it divided by the total area of the plane, and that's how we would find eta, just in the same way. You would take just one of these, right? Just the magnitude of either one of these, eta over the area of just one of these, and because they're supposed to be equal charge densities, but they're supposed to be equal planes, we just double that value. So it's a really useful one though, right? And we'll keep coming back to this and we'll keep using this because this is a fantastic way of generating a constant electric field of a certain magnitude, and capacitors, it turns out, we build a lot of them. So this is not an unreasonable thing for us. Now, we have our first whiteboard problem. And this is loosely called breakdown voltage, which is not a very scientific term. It's more of kind of a fun term that you'll hear sometimes when you're seeing a bunch of sparks fly out of things. One of the places that you might see something similar like this happen, though, is if you have like a high current device like a vacuum cleaner, for example. If you take a vacuum cleaner and the cable that you've got with that thing, if it doesn't have a ground plug to it, so if it doesn't have the third prong on the bottom, if it's just got the two, let's say you accidentally left your vacuum cleaner on, you turned it on before you plugged it in. One of the prongs is ever so slightly longer than the other, or maybe you come in at an angle, and you might have seen before, maybe a short blue flash of light comes out when you try and plug that thing in, right? What happens there? Well, there's two prongs, there's two contacts on the inside of the wall, right? Both of those contacts are pretty high voltage, realistically. So I plug in one of it, and one of them makes contact first. Now, we have this whole big long sequence, but it ends up with one high voltage point and one low voltage point, and they really want to meet, right? There's a really high voltage difference between those 2 points before the second plug has made contact. And because it's a very high voltage and a very short distance, we get what's called the breakdown voltage, and it actually creates a plasma out of the air between those 2 plugs. And that plasma is now very conductive, right? Which is why it forms, because the electricity really wants to go through. But that's what shoots out some sparks. And this is not something that I recommend trying out, right? You'll occasionally see these things kind of if you're plugging in devices that immediately are taking advantage of that current. But it's not something that I recommend. You'll scorch the contacts and there's always a risk of fire. And the disclaimer is don't actually try this at home. But there are certain demos that will actually recreate this. As we see in our picture here, that's actually exactly what's happening. We have 2 very big plates, parallel plates, conveniently, and what's down here in the bottom is a little hand crank static generator. So you turn that thing and it creates a difference of charge. Positive charge goes along the red wire, negative charge goes along the black wire, and you end up creating this parallel plate capacitor that you can keep charging and charging and charging and charging until we get to the breakdown electric field strength, right? Which is a little bit more scientific. Once we get to an electric field strength of 3 times 10 to the 6th, the air breaks down into plasma, creates that brief spark, and then we're back down. That allows a bunch of current to pass through. We're back down to a neutral charge, and then we've got to crank it to charge it up again. So let's make this a little bit easier. Instead of circles, we're going to talk about squares. So I've got 2 big squares that are pressed right up against each other. How many electrons do I have to move from one to the other to create a spark between these 2 disks? So if you're working from recording, go ahead and work on this one, and I'm immediately going to jump into working a solution for anyone curious on that. So what we have we're working with whiteboard. Let me do that a little bit thicker so we can actually read it. Whiteboard 23-5. Okay. So let's first start by drawing a picture, right, as I like to do. And I'm going to take a side profile of this thing. So we've got two squares face to face like this, but instead I'm just going to draw this out something like, I want to get this as a line so it actually looks kind of straight, something like this, right, roughly speaking. Now, one of these has a surface charge, I'm going to call this positive eta. The other is going to have a surface charge negative eta, right? But that magnitude eta is actually what we're looking for. That is the magnitude of our surface charge density, and that's what we're actually going to plug into our equation, right? We are looking for a specific spot where our electric field reaches this point, right? We know that the electric field reaches 3 × 10⁶ newtons per coulomb. And my electric field, I'll go ahead and draw it out. It goes from positive to negative, from positive to negative, something like that, right? Almost looks like an ice cream sandwich or something. That's what our electric field should look like. We need to find what is, roughly speaking, that charge that makes this E happen. Okay, so let's work from there. E, because we're dealing with a parallel plate capacitor, is equal to eta divided by that permittivity constant, right? I'll call that E naught. Okay, well, that tells us something about the charge, but the charge is not what I'm interested in. I'm interested in the number of electrons, but each electron contributes something of a charge, right? So let's take the middleman first here. Let's talk about the fact that eta is a surface charge density, so that'll be equal to Q divided by A. We also know that the A is 4 by 4 centimeters. So that is a value that we have. Now Q is what I'm after, right? Because Q is being made up of a bunch of different electrons. If I take all of the electrons from the positive plate and move them over to the negative plate, let's say they start at neutral, right? If I pull off all of these extra electrons, that went from neutral to a lack of a bunch of negative. So now that's going to be positive. We push all of those extra electrons onto the negative plate, and that's how we get this difference between the two. How do we find that difference actually? Q is going to be equal to the number of electrons times the charge that each electron contributes. Now, realistically, I know that this is going to be positive and negative, but what I'm really left with here is that the positive has what we call electron holes, places where we expect electrons to be, but they're missing, so we have a positive charge left over. On the other hand, we have a bunch of extra electrons, so either way, I don't really need to include the negative in the E because I'm just calculating one of these values anyways. We'll just leave it as E for now. But with all of this stuff, we are solving out for our value capital N. So let's go ahead and plug in Q. And what we find with that is that eta is now equal to NE over permittivity constant. Now let's plug that back into our electric field equation up here. And what we get is E is equal to NE over little e. Oh, whoops, I made a mistake here. And nobody's here to catch me when I'm making these mistakes like this in a recording. So this would actually be, I'm plugging in for Q. So this would be NE over A. That's what I should have done, right? And that's how we get this result right up here. So with that now, we can rearrange this. We're solving out for our value for capital N. We plug in all of these values together. And what we should find at the very end of this thing is 2.655 times 10 to the 11th electrons. Just like that. So let's go ahead and box this off before we get into the next problem. But before we get into the next problem, I've got a couple more details to look at here. So we looked at this last time as well when we're discussing like acceleration and everything else, right? Naturally, Newton's second law, force is equal to mass times acceleration. We had to have known this was coming. We're going to eventually find for an acceleration. But remember that we can do a bunch of different stuff with kinematics. So as long as our acceleration is constant, which would be from a constant electric field, or a uniform constant electric field, in a case like that, then all of our old kinematics equations actually come back, and they're still useful for us, right? Remember that all of these things assume that acceleration was constant. If acceleration's not constant, the equations get a little bit more messy. There are still equations that describe those, but they're not ones that we've covered because they start adding more and more and more terms, and it just becomes too much of a headache at a certain point. So, in cases like this, remember that the electric force is just another force, right? It's something else acting on our particles, and we can calculate that stuff out just like we always have. So, we can give it a shot. Let's say that we have an electron in a uniform electric field, right? So our constant acceleration rule applies. And we start at 2 times 10 to the 7th meters per second, which is an appreciable fraction of the speed of light. And we speed up to 4 times 10 to the 7th. And we do that in a distance of 1.2 centimeters. What is the strength of the electric field that we need to be in to make this happen? So here's what we can do. We don't have any idea what any sort of direction is in this problem. They don't tell us, so what we're going to have to do is just kind of draw our picture and make some decisions for that ourselves. So this is whiteboard 23-6, and what I'm going to start with here is my little electron, right? Green ball with a minus sign in the middle to remind myself. Now, because we're dealing with an electron, as soon as somebody says electron, there is a charge and a mass associated with that electron, and that is always going to be true. Every single electron has 9.11 times 10 to the negative 3rd kilograms of mass and 1.6 times 10 to the negative 19th coulombs of charge. Every single one, no exceptions. No differences in decimal or anything else like that. They're always exactly the same. So that makes it a little bit convenient, right? That's always a little bit of extra information that we have should we need it. But anyways, we start at a position x0. We also start with a velocity, or a speed rather, but I'm drawing my picture like this. Call that y, call this x. I'm starting with a velocity v0 is equal to 2 times 10 to the 7th meters per second. So we start like that, and then some distance later, we are now zipping by even faster. We are now at a position x1, call it, but we are moving the longer velocity. v1 is equal to 4 times 10 to the 7th meters per second. And this is just useful for writing out all of my details, right? A nice little picture. And the question is going to become, if you're watching this solution, take a guess, what direction should my electric field be pointing to make this happen? I'll solve this problem and then I'll answer that at the end. So between these two positions, I don't have any idea where x0 technically starts. Maybe it's 0, maybe it's 50, I don't know. But I do know that the difference between the two, delta x, is equal to 1.2 centimeters. And really, that's all we'll need. So you might notice we have a v0, we have a v1, we have two velocities, we have a change of position, and we're interested in acceleration. Well, we're not interested in acceleration, we're interested in electric field, but that is going to exert a force which causes an acceleration. So we can wrap it back around to the value that we're actually trying to find, right? So let's do just that. Let's use force to tie together these two values to kind of remind ourselves where we're headed with this. Force is equal to Q times E, that's the electric force, causing an acceleration like this. And if we look at this, we can say, okay, well, Q, that's a value that I have, right? Because it's an electron. M, that's a value that I have because, again, it's an electron. The electric field is really what I'm after, and to get there, I need my acceleration. So I go over to my handy-dandy kinematics equations, and I can say, all right, with two velocities, acceleration and delta x, what equation ties those all together? I don't have any idea on the time, but I don't need it because I can just immediately jump to this equation right here. v1 squared is equal to v naught squared plus 2a delta x. We have v1, we have v naught, we have delta x. We can find acceleration, right? When we solve out for that, we should find an acceleration of 5 times 10 to the 16th, which is not a small value in its own, meters per second squared, right? And a lot of that's attributed to the fact that it's such a tiny mass and what we're going to find a pretty large electric field. So there's our value for acceleration. We can come back up to here. We're rearranging this thing, so plug that in up here. Rearrange this so that electric field is equal to ma divided by q. And what we find at the very end is that electric field should be something like 2.847 times 10 to the 5th newtons per coulomb. Something just like that. Okay. And again, clear out some space for the next problem. Okay. So immediately we're going to jump into this next one, right? That was kind of a warm-up with our old kinematics equations, but you remember a lot of what we spent our time on was actually parabolic motion, right? Or projectile motion, launching things through the air, watching it change in maybe both directions. But in a case like this, let's see what we've got. I've got two parallel plates, so that immediately tells me that the field is uniform between these two plates, right? My constant acceleration equations do apply. Okay, well, they're spaced apart by 2 centimeters, and we already know the field strength, so we don't need to calculate that or anything else. We already know what the electric field strength actually is between these two. The picture doesn't indicate the direction of the field, but we'll draw that on our own picture. We're having some fun in the lab. We're launching some electrons through these parallel plates, right? We're trying to see how fast could we possibly get these electrons launched in. If we launch them at 45 degrees, how fast could we launch them and still not hit the top plate? That is to say, the highest point we get is something like 1.9999999 centimeters. Why don't we just round to 2? So I'm going to copy my picture because I'm going to make some drawings on this thing, right, to make this a little bit more clear. It's been a while since we've done any sort of parabolic motion like this, so maybe it's helpful to have some reminders here alongside us. Shrink it down just a little bit, not too much. We'll upscale it a little bit. Want to make sure I've got plenty of room to draw on this thing. So this is whiteboard 23-7. Okay. So the first thing I want to do, I know I'm getting launched here, but I need to think about what do the forces look like as they're acting on this? Well, my electric field should point from the positive charges to the negative charges, right? Something like this. Okay, well, if the field lines are pointing up, remember that I'm dealing with a negative charge. This Q is less than 0. What that means is that the force we feel is going to be opposite the direction of the field lines. That is, the electric force is going to be pointing straight down like this. Now, this is pretty important, right? Because if it was pointing the opposite direction, we're never going to get off this thing, right? We're always going to be, we're going to fly right into the negative plate and we're never not going to touch it if the force was going the other way. But as long as the force is pointing down like this, you might remember that we're probably going to end up with something that looks like this, right? Kind of a parabola. And maybe I drew that one a little bit high. Let me scale that down a little bit more. We want to end right around there, right? And then we would fall back down the other way. But I really don't care what happens on the tail end of this thing. I'm actually a lot more interested in what happens right here at the peak of my arc. So that's the kind of motion that I'm expecting. I'm trying to say, let's make the maximum height we achieve 2 centimeters, right? Any higher than that and we hit the plate, but, you know, within a little tiny decimal point, we are below 2 centimeters. So let's just say 2 centimeters. Okay. Well, in a case like that, I need to figure out what variables I have and what's actually going to be useful for me here. So if I'm talking about projectile motion, I see my electric field is just pointing up in the y direction. I should draw that on my picture while I'm here. There's no forces acting in the x. And while we're talking about forces, gravity is really not going to make a difference here. You would find that if you try to include gravity, you're going to end up with a force that's 10 to the negative 30. It's not actually enough to make any sort of real difference here. So instead, let's just focus on the electric force for now, and let's assume that's the only thing pulling us down. Okay. Well, the special parts about dealing with an arc like this is that I know information about my initial state and information about my final state, right? So let's say we remember that at the top of the arc, my velocity in the y direction, so call this v1y, or actually, no, v1y is fine, v1y. v1y ought to be 0, right? It should be 0 at that point because that's when I turn around. That's when my velocity stops going forward, it hits 0, and then it turns negative again as I fall back down. So we know that. We also know that my initial velocity in the y direction is v0 times sine of 45, which we can plug in for decimal if we want, but I'll leave it for now. Okay, we also know, as we're going along with this thing, that delta y is 2 centimeters. And this kind of looks a lot like the last problem, right? I've got two different velocities. I've got a delta y. Well, I'm looking for this v0, but I have some details about the electric field. And if I have details about the electric field and details about the charge, I could find the acceleration. So let's do that. Let's start by again saying force is equal to Q times E is equal to M times A. And there's like an implicit j hat attached to a lot of these variables that I'm just not including, right? All of this stuff that I'm talking about is in the y direction, so keep that in mind. If I see a positive or negative, that's positive and negative in the y direction. So what I'll do then is I want to rearrange this to find my acceleration. A is equal to QE divided by M. And for Q, I am going to end up plugging in my negative 1.6 times 10 to the negative 19 coulombs because I expect my acceleration to be going in the negative y direction, right? It better be negative when I actually solve out for this thing. I can't just take an absolute value of this one or else, again, we just fly into the negative plate every single time. So when I plug all those values in, I should end up with something like negative 1.756 10 to the 15th meters per second squared. Okay, now we have an acceleration, we have a delta y, we have v0, we have v1. We can plug all of this stuff together into one equation, and let's go ahead and write it over here. v1y squared is equal to v0 y squared plus 2a delta y, and it's not a minus sign here, right? The minus sign is included in the acceleration when we end up plugging that in. So I know that this value right here is 0. That's out of the way. I can plug in v0 y squared is actually v0 squared, sine squared of 45. And I'm just going to leave this thing as this for now. I'm not going to plug in any values yet. We rearrange this thing, and what we'll end up finding if we solve out for v0 is equal to square root of negative 2a delta y. Again, don't worry, we're not coming out with complex numbers right now. That a is negative. Divided by sine of 45. That square root just killed off the square. Plug in the values. Again, we're expecting a positive answer here by the time we all finish this stuff. And we should find something like 1.185 times 10 to the 7th meters per second. And there's our final answer and expression. All right. Good progress so far. So, what happens if we were to, say, for example, find a non-uniform field? Maybe it's curled, maybe it's a point charge or something like that. What do we do about it? Right now, we don't have a better answer than to scream, right? Just scream at your computer or something. But luckily, you probably won't see these, at least not very much, because for the most part, we don't have the tools to deal with these yet. Think back to what we did in kinematics when we ran into the same issue, right? What happens when we deal with like a curved slope or something like that? We no longer use kinematics to describe it. Instead, we switched our description over to energy, actually. And what we'll find is that these same problems in electromagnetism, we solve in energy in the same way, right? We still have the same solution to those problems, but we're going to wait for another couple chapters to actually talk about energy when we're talking about electrics like this. We'll have potential and potential energy, two separate values actually, that we'll use to describe the problems where acceleration isn't going to be constant. Energy kind of takes up the torch on that one and makes these problems a lot more bearable to solve. So, instead, let's turn our attention back to dipoles for a little while. Think what would happen if we were to put a dipole into a uniform electric field, right? Like from our parallel plate capacitor. Well, in a case like that, the electric field acting on each charge is going to be exactly equal. So if I'm thinking about this in terms of net force, the negative charge will feel a force one way, the positive charge will feel a force the other way, but they'll both be equal and opposite. The net force on the dipole would be 0. However, if it's not already aligned to the field, you can kind of see this already. The force does not just go along the axis of the dipole moment. We would see a torque acting on our dipole, right? And torques have been one of those things that we might have to drag up from the depths of our memory. It's been a little while since we've talked about it, but it is here to return. And what happens here is that as long as we're not aligned with the electric field, if we are anything but directly aligned either forwards or backwards, if we're anything but directly aligned with the electric field, then we are going to experience a torque. The dipole is going to try and right itself to align back with the field again. But it's not going to actually move anywhere. It's just going to spin in place because, again, the net force is going to be 0. So how do we actually describe that torque? Well, the easiest way is to use a cross product. P cross E will equal the torque acting on the dipole, where P, remember, is not momentum, it's the dipole moment. However, when I'm looking at this picture, I don't really have a good sense of how to deal with that, right? What are these two vectors? Do I have the lengths? There's some messy things here. So remember that another way to express the cross product is just PE sine of theta. You take an absolute value and then you figure out the direction using the right hand rule, right? My right hand. I know it's flipped on camera. So, is there always going to be a torque? Well, no. We could have a non-uniform field, and remember, we're not talking about kinematics. This is just forces. We could have a non-uniform field, and in a case like that, well, if I have a positive charge, the charge is going to be having a field as 1 over r squared. So the closer charge will feel a greater force than the farther charge. And in a case like that, negative q is going to be more attracted to the point charge than positive q is repelled. We would see a net force pointing to the left. There's not a torque here because it is aligned with the field lines, right? But there is still a net force. What about this? What if I tilted my dipole a little bit? Well, in a case like this, now there is actually a net force and a net torque acting on my dipole at once. But this suddenly becomes a much more complicated problem. But we can handle these things because, again, these are mostly just point charges right now. So let's try that on a problem. We're not dealing with a point charge, but instead an infinite rod of charge, right? Which we have an expression for what that electric field looks like. So what we're saying here is we have an infinite line of charge with lambda as my charge density and a dipole with negative q and positive q as my two charges on either end. Now, how we define some of these variables is going to be a little bit important for us. So what we have here is r goes from the rod to the middle of the dipole, right? And that's important. I need to talk about those points. But I've got two questions for dealing with this thing. First, is the dipole attracted, repelled, or doesn't feel a force from my rod of charge? And then once I do that, we've got some algebra to do here to figure out what is that force actually going to look like, close by and far away, right? Is it different? Let's find out. So let's go ahead. Oh, I forgot to draw some space around this thing. I want to make sure that I keep these. I know we've got a lot of problems to deal with on this lecture in particular. So I do want to make sure we keep those separated enough that it's easy to read later. What I would like to start with, though, is drawing out what I've got going on here. So this is whiteboard 23-8. And we start with our infinite, or nearly, rod, right? That has a charge density, a linear charge density, specifically lambda. And I know the electric field is radially outwards. So it looks like this on the right side. It looks like this on the left side, but my dipole's over on the right side. So that's the only side that I really care about right now. Okay, and speaking of that, I have my dipole here. I'm drawing this thing with plenty of space right now, but it doesn't necessarily need to be that large. We're going to space this thing out eventually. This is positive Q. This is negative Q. And I like to just kind of go through my process of drawing a picture because I recommend you do the same. Even if a picture's already given, a lot of the times I like to draw up my picture anyways, just because I have to go through all of the steps of thinking about all of the different pieces, right? Why did they include every aspect of that picture? Sometimes it's worthwhile to question that. Okay. And then we said that our value R away from the rod is going to look like this, roughly speaking. Here's R. Goes between these 2 points. Okay, so we've got our work cut out for us. Now, one of the things that I can see here, remember that the electric field from an infinite rod is always going to be 2k lambda over R. Right? And what we've got here is, well, we're not actually R away. Neither charge is actually R away. They're a little bit separate from that. But what I'm going to need to do for this problem to start with, I need to find the net force. I already see that there's not going to be a torque because my dipole is aligned with my field lines, right? My dipole moment, in fact, looks like this. In purple, not that we really need it right now, but we'll eventually get there. So I'm going to try and find the net force on each charge and then combine those together for the dipole as a whole. So let's start in green here. I'm going to call this F negative. This is, or F minus, this is the charge acting on, or the field acting on negative Q. So that'll be negative Q times the electric field that we feel at that point, right? And again, I should be better at this, drawing my axes on here so we can keep track of it. Y doesn't really matter, but X kind of does. Okay, well, what is the electric field at that particular point? Well, it's going to be 2 times K times lambda, but then we need to be careful. That distance is not just R, it's a little bit closer than that, right? We can see we shave off a little bit from R. We end up right there instead of being all the way at R. So this is going to be R minus S over 2. That makes it a little bit of a stronger field. Okay, now I'm going to do the exact same thing with F plus, right? The force acting on the positive charge. So this will be positive Q times E. Again, same arguments being made. 2k lambda R plus S over 2, right? We get a little bit farther away than R. Okay, and then just like I said, we want to combine these into some net force, right? Something like this. So F net is going to be equal to F plus and F minus. One of these is negative, one of these is positive. We want to leave it like that. Again, these are all kind of in the X direction, right? So I put these two things together. Now, they share a lot of similar terms. 2k lambda Q. Let's pull those out. 2k lambda Q. And now in brackets, I'm going to have what's left. So my first fraction is R plus S over 2, 1, minus 1 over R minus S over 2. Those are my two terms. Okay, and that is an accurate expression, right? That's technically all we could ask for. But we would like to put this in terms of the dipole moment P. And honestly, this is still kind of clunky. So here's some algebra simplification that I'm going to try and do. Let's start. I'm going to leave the constants alone for now, right? There's nothing else we need to do with these. But what I'm going to try and do on the inside is combine these all into one fraction together. So we get that And we get that, right? R plus S over 2 times R minus S over 2. And if we do that, then on top, we're going to end up with R minus S over 2 minus R plus S over 2, which is a few minus signs to keep track of. But that's okay. So piece by piece, the bottom, that's just going to multiply together. I'll get to that in a second. But I have R minus R. R's will cancel out. Negative S over 2 minus S over 2. That's going to become negative S. So let's multiply out that bottom term and replace what we just found on top. So this is now going to be R squared minus S squared over 4. That is under negative S, right? I'll put that in parentheses. So it's not minus or anything else like that. It is multiplying by. Now, one of the conditions that we had in the problem in part 2 there, we were talking about what happens when R is much, much larger than S. And the reason that we couldn't really neglect it when we were over here, we're going to find kind of a similar result during the end, but one of the reasons you can't really neglect it is because imagine it's a 10 to the negative third difference. 10 to the negative third is not going to be a lot, but it is still going to be something, right? Though at that point, stuff's getting a little bit extreme. But let's say it's maybe only 10 to the negative first or 10 to the negative second. Something like that is still a pretty reasonable value, right? That's going to be a difference that actually ends up mattering. However, if we were to square that, then that order of magnitude essentially doubles, right? A 10 to the negative second becomes a 10 to the negative fourth. And that kind of difference now is much, much smaller. I have a much easier time sleeping at night neglecting terms like that than I do for something 10 to the negative second. So that's what we're really looking for, right? Once it's in this state, once I have some value squared in the difference between those two, now I feel a lot more comfortable saying, okay, let me take this approximation. And before I do that, let me finish this. I'm going to write this while I talk. I can cancel out, I can take that approximation that S doesn't really matter at the very end, but not until I've already found, so this is 2k lambda, S times Q is just P, right? Our dipole moment. So here's our expression for any distance away from this infinite rod. But we say if R is much, much greater than S, not just greater than, but much, much greater, right? At least an order of magnitude difference, but hopefully more, then S squared over 4 is really not a big enough difference to matter. I can neglect that term and come down to that the force is approximately negative 2k lambda P divided by R squared. And I want you to remember here that for one, this is only when we're talking about very, very far away. But we have a couple other things that are actually going to go into this at this point. For one, let's look at the solution we just found. Remember that Newton law that said an object exerts a force and it's going to feel an equal but opposite force. That's still a thing here. Let's talk about what that might mean for this then. If the rod is acting on the dipole, we expect it to look something like the field did, right? So 2k lambda over R. Well, we don't see that. But then in the same way, we could actually say, okay, well, if the rod is acting on the dipole, in just the same way, the dipole acts on the rod. And we saw last time that the field coming from a dipole is something 1 over R cubed. So, okay, well, then the force on the rod would be 1 over R cubed, but we don't see that here either. It's kind of this funny thing where we might expect either one of these options, but we actually meet somewhere in the middle as a 1 over R squared. And at first, that probably didn't catch your eye, because realistically, if we're looking at lambda, lambda is kind of like a charge, and P is kind of like a charge again, and then over R squared, of course, yeah, Coulomb's law. But that's not what we expected to find. If we thought about this a little bit more, neither of these are point charges. One is an infinite line of charge, and the other is two opposite but equal magnitude charges connected together very closely. So it's this fun kind of result where you get kind of a halfway in between both of them at the very end. And that might not be as clear had we just left it as it was before we took this approximation of what happens when we're really far away. So I just think it's a really kind of cool result, right? It's a fun little thing. There are some algebra tricks to get here that maybe were not a little bit, not very clear. That might have been a little bit more of a struggle for you. I'm not super worried about that. If this was a little bit strange, as long as you can follow, you're in a pretty good spot. Getting these algebra tricks, that takes quite a bit more practice. So don't feel too down or anything else if that was a little bit strange how there's a little bit of intuition, a little bit of creativity that comes with that really only gets trained with more practice on these problems. So let's go ahead and box that one in. Now, here's the last one, and this is one that if you were in the second lecture, we got cut a little bit short before I could really talk about this one. And this is definitely one of the more challenging problems of the bunch. So here's what we've got. We're back to that uniform field. We actually have the same picture as before, right? We're in a uniform electric field. We have an electric dipole with a dipole moment P between charges minus Q plus Q. They've each got a mass M, which is important, right? Keep that in mind. And imagine that this thing was aligned with the field, but then somebody, pulled it up a little bit and then let it go. So it's a small angle, and what's it going to do? Well, it wants to align itself with the field. There's no net force acting on this thing, so it's only allowed to spin essentially in place, spinning about the middle, by the way. And if it's spinning just about the middle like this, back and forth and back and forth and back and forth, this is what we would describe as simple harmonic motion, right? Something we haven't seen for a little while. But what I want you to try and do here is, you haven't attempted this problem already, see if you can come up with this expression. But this is a little bit more of a difficult problem. So let me talk through what I think. Let's find ourselves some good space. And I might as well pull the picture over with me. Since we've already got this thing, let's get rid of that point for now. I'll redraw that one. We might as well just copy this picture over. I would still recommend, if you're doing this on your own, draw this thing out. I'm just trying to save a little bit of time here while I'm on camera like this. So what we've got, I'm also going to shrink this down just a little. Come on. There we go. Shrink it down just a little because I'm not actually going to draw on this picture too much. I don't have a lot more to say, really. So, whiteboard 23-9. So we've already kind of stated it's going to spin back and forth. It wants to align itself, but because there's no friction or anything, it's just kind of pivot back and forth like this, right? Back and forth and back and forth and back and forth. Same thing over here. Back and forth. That's how it's going to go this entire time. Okay, well, let's talk about the things that we actually have. We are given the electric field, the dipole moment P, the charge at either end Q, and the mass of each charge M. We need to find the period of oscillation capital T. Okay, well, I know it's been quite some time since we've talked about oscillations, and we only talked about those honestly in kind of a limited context, right? We did end up using them quite a bit while we were on them, but unlike kinematics, they weren't showing up every single chapter. So this might be a little bit more review than some of the other things have. T, if I could get my draw pad to work. It's a good thing to see that the technical issues are not exclusively limited to the live sessions, even though it seems more frequent there. But at the very end, you might recognize this equation. The period of a simple oscillation is 2 pi divided by omega, the angular speed. Well, that looks pretty simple. And deceptively simple, in fact. We've got a few other things that we're going to need to do before we can actually get there. So let's do this. Let's think about all the different pieces we have. Where's that omega going to show up? Well, let me see if I can't get through a few of these things. If you remember from our old equation sheet, we had this old expression that said d squared x over dt squared, which was the second derivative of x, if we were talking about, for example, a spring, is equal to negative omega squared x. Can we make our expression look like this in some way or another, right? We do have some integrals to deal, or not some integrals, but some derivatives to deal with here, but we're not actually going to need to do too much for. So, okay, before I get there, let me think about what's actually happening to the dipole. I've got a dipole misaligned in an electric field. There is a net torque acting on this thing. And I'm not going to try and use the cross product because that's going to be really messy. But instead, I can say, okay, well, the torque acting on this thing would be equal to P(E) sine of theta. Okay, well, I have P, I have E, I have sine of theta. What else is the torque going to do? The torque is going to tell me about how fast I'm about to start spinning around, right? Or other words, my angular acceleration, I alpha, where I is the moment of inertia of my dipole. Okay, and again, because there's no net force, because this thing is just going to be spinning around like this, my pivot is right here in the middle. So I'm going to draw this off to the side, but I'm not going to plug it in immediately. What we see then is that the dipole, I've got 2 point masses essentially, right? I've got a mass, so this would normally be mr squared for each point. However, I am a distance s over 2 away. So that's s over 2 squared. And then we have 2 point masses that distance away. So this will be 2 times m s over 2, all of that squared, which let me just simplify that real quick. That's just going to come into ms squared over 2. I'm not going to plug that in yet, right? I'm going to leave that there for now because I is a lot easier to write than this thing. So let's come back to that idea. But if we're coming back to our torque equation, I really don't, torque is kind of done, whatever that thing is. P(E) sine of theta is equal to I alpha. Alpha, if we might remember, angular acceleration is the second derivative of position. That is to say, alpha is equal to d squared theta over dt squared, which I realize it's not x, but we've done this, right? That's exactly what we have up here. Here is where we're going to find our omega from. So going from here, right, I need to figure out what I can do with this thing. I can rearrange my torque equation to make this thing work. I can say, okay, in a case like this, d squared theta over dt squared is equal to, let me rearrange this, P(E) sine of theta over I. And this is almost there, right? But here's an issue that I run into. P(E) sine of theta over I, I don't have theta. I need theta back, right? And this just isn't it. So, oh, and one more thing that I forgot. This should have a negative sign out front. And I ran into a little bit of an issue with this the first lecture around for anybody that was involved in looking in on that. What I've got here, this is based on my definition of theta as I've got it. When theta goes up, in my definition of the right-hand rule, when theta is going up like this, P cross E is going into the page, negative, right? So a positive theta leads me to a negative torque. A negative theta, if this went around the other way, if it went clockwise beneath the positive x-axis, that would give me an out of the page, that would give me a positive value. So that's where this negative sign is coming from. It's a right-hand rule. Right-hand rule. But let me talk about that towards the end here and why, if you didn't grab that the first time around, it's not going to be that much trouble. So negative P(E) sine theta over I. But again, so I said, okay, this is not just theta. If it was just theta instead of sine of theta, I'd be done. I could solve this thing. I could just set this equal to omega squared, but I can't. However, we go back to the problem real quick and we say, okay, small angle, that's drawing instead of highlighting, small angle theta. Small angle theta. That means one thing and one thing only. We can take the small angle approximation. And the small angle approximation, go ahead and write that out. Small angle approximation, in my very poor handwriting, says that sine of theta, as long as this is small, is just about equal to theta. Right? As long as I'm below 10, maybe 20 degrees or so, this approximation works pretty well. Right? It loses a little bit of accuracy, but honestly, it makes the problem solvable. So what else are you going to do? Then we can say d squared theta over dt squared is actually, or approximately rather, P E theta over I. Which, wouldn't you know it, looks a lot like this. So, using that information, we can basically say, okay, get rid of the rest of this stuff, strike the theta, because theta is a changing value, right? It's a function that is not constant with time or anything else. It's constantly oscillating back and forth between these 2 points. But omega squared and PE over I, those are the constants multiplying my functions. I can pull those out by themselves, and I can say that omega is equal to the square root of PE over I, which at this point I'm getting pretty close to the end of the problem, so I might as well plug in for I. This is 2PE over MS squared. And there we have our expression for omega, right? Deceptively simple is what we said about that expression. So that's where we are with this, right? We plugged in all of our things. We found what omega should actually be. Now we can take this all the way back. I'll highlight this in red. All the way back up here. Go ahead and plug this thing in. What do we find? We should end up with something. And there's one last thing that we could do with this thing if we want to actually simplify this the rest of the way. I need to be careful with how I describe these things. But I'll plug this in. I'm essentially just flipping the omega. So this turns into 2 pi times square root of ms squared over 2pe. Now I run into one last issue before I end this thing. What do they want us to find this in? Q, S, E, and M. The last thing that I'm going to need to do is replace this P with, I should have had, we're not given P, we're given S instead. My mistake. I saw P on the chart and I should have read those lines a little bit more closely, but it doesn't end up making too much of a difference because P is equal to S times Q, so one of the S's on top will cancel. And I'm just going to leave, I know I could cancel out one of the 2's, but I'm just going to leave the 2 pi out front. Right? Who's going to stop me? And there is our final expression for the period. So this is certainly one of the more complicated problems, right? I'm not going to fault anyone for being a little bit spooked from this one. It is certainly a lot more involved. It's remembering some of our second derivative stuff, things like that. So I know it's been some time since we've looked at any of this stuff, and it's probably not very familiar at this point, but that's okay. We're not going to have to do a ton of these things. We're mostly going to be focused on just dealing with like torque and moment of inertia a little bit, but to deal with oscillations like this again will be maybe occasionally, but not too much. But anyways, with that, we're going to close out. That is the very end of our 23-3. That closes out chapter 23. Next time, we look at Gauss's law, which we will find is a fan favorite, I think. So, until then.